Good morning, students. As a part of online classes, we are dealing with the advanced material subject. In this advanced material subject, myself is Dr. B. Suresh Babu, working as a professor in Mechanical Engineering Department in MBR College of Engineering and Technology, Paritala. In this session, let us have a explanation on stresses on laminates. This is in continuation with the previous class only. As the previous class, I have explained about stress, strain, and relationship between the stress and strain with respect to Hooke's law. And we have solved 4 types of problems. That includes Young's modulus, bulk modulus, percentage of elongation, and relationship between the Young's modulus and the parameters. That is how change in length will affect the will related to the Young's modulus. So in this class, in connection to that one, we are going to learn another a few concepts based upon the same, but here we are going to take a laminate as the one of the major key point to analyze the stresses. As this is the syllabus, I am regularly giving this screen. Why? Because it is a introduction and generalized Hooke's law itself is a large content is there to explain, so that you can have a better understanding on the coming concepts. If you observe this one, if you to understand this orthotropic laminate code. So in connection the syllabus, we are going to concentrate on this one. Let us have a look on this one. Okay, this is try to understand here students, Hooke's law in terms of stress and strain. This derivation already we have derived in the previous class. Let us have a glance on the content. Hooke's law in terms of stress and strain is stress is directly proportional to strain. In terms of the dimensions, F by A is equal to Y into delta L by L. What is the F we are going to observe is A is the area of that one, Y is the Young's modulus, delta L is the change in length, and L is the original length. F is the pressure. F is the pressure. If you observe Young's modulus, due to the pressure, it is going to be expand. That means laminate is going to expand. In bulk modulus, if we consider, the laminate is going to be compressed because there is a compression pressure is there, expansion pressure is there. In Young's modulus, we are going to consider expansion, that is expanding the pressure, that is force is applied and laminate is going to be expanded here. If you observe that bulk modulus, it is going to be compression. So that is the 2 points to remember. I repeat, this formula I have written, and Y is equal to delta L by L. If you represent it with K, K is going to be called as a bulk modulus. So let us remember that one. So the constant of proportionality is called elastic modulus. That is F by A is equal to Y into delta L by L. Delta L by L indicates between force applied and area on the laminate. Area is length into breadth. and y is called Young's modulus constant. Delta L is a change in length by original length. Delta L is change in length. L is the original length. Try to understand here. The constant of proportionality is called elastic modulus or Young's modulus. If the same unit as stress, y is a property of a material used. So this what we have learned in the previous class. Then, as we all know that I'm regularly saying, Hooke's law is stress is directly proportional to strain within the elastic limit. Hooke's law holds up to a maximum stress point, and that point is going to be called as the proportionality limit. I repeat once again, in the graph we are going to observe, already I have explained number of times, based on that graph there is a 5 limits are there. Proportionality limit, elastic point is there, next one is yielding point is there, next one is breaking point is there, fracking point is there, that means fracture point. So these materials are going to be vary from ductile. These points vary from ductile material one type of property and brittle material one type of property. To explain these two differences, I am try to explain with the help of this graph. Already, if you observe the graph, you can see it on the screen. Let us have the continuation of the concept. Let us Hooke's law holds up to a maximum stress called as proportionality limit. Beyond the proportional limit, what happens? If the stress exceeds the proportional limit, the strain is no longer proportional to the stress. The solid will return to its original shape when the stress is removed. That means it is the point of a proportionality limit. At proportionality limit, when the stress is removed, it comes to its original shape and original properties. So that is how the proportionality limit is limited. Next, elastic limit. When the stress is less than the elastic limit, removing the stresses will return the solid to the original shape. If the elastic limit is surpassed, the solid remains permanently deformed. That means if you apply a material, if you material is exposed to a force or a load, at one point of time, if it crosses elastic limit and that load is removed at that stage, material will directly deform to its another shape than its original condition. That state, that point is going to be called as the elastic limit. That means the point at which where more load is applied than the elastic limit, that point is going to be called as the elastic limit. That means where the property does not regain its original shape after removing the load also is going to be called as elastic limit. This point I already have explained number of times. Proportionality limit is the limit where we can add load up to that point. Beyond that point, if you add the load, it will go to the elastic limit. So before going to the elastic limit, if you want to remove the material, you remove the load, then also it will come to its original shape. Then that is going to be called as a proportionality limit. Next one is ultimate strength. It is the strength. If the ultimate strength is surpassed, the solid fractures. The ultimate strength can be different for tensile and compressive stresses. So already we have discussed in the previous concept only. There are Young's modulus, one type, different types of stresses will be there. Tensile will be there, compressive stresses will be there. We have considered based upon the fundamentals, compressive stresses for the bulk modulus I have explained in the previous class, and Y for the tensile stresses. So if you observe the ultimate strength, how it will be for a ductile material and how it will for a brittle material. The same concept for elastic limit and proportionality limit. If you observe these two graphs here, this is going to be called as the tensile strain, and this is going to be called as a tensile stress. This is called proportionality limit. This is called elastic limit. This is ultimate strength, and this is called as a breaking point. So this is, if that means, if you observe, after beyond the ultimate strength also, material is going to try to deform on its own. That means in ductile material is going to be deformed, or before it will fail, it is before it is going to fail, it is going to get deformed. That is the thing to be understand here. If you observe the same for a brittle material, this is tensile strength, this is tensile stress, this is proportionality limit, this is elastic limit, and this is ultimate strength and breaking point. Here, brittle material fails suddenly. Due to that one, what happened is, after removing the load point, here ductile material has given an indication that its stresses are going to be decreasing. But here, at ultimate strength only, the material is going to fail in brittle material. That's not happening. This is the first difference to be observed. Next difference is, based upon this analysis, we can understand that ductile material gives a warning. That means beyond that ultimate strength also, material is tried to in functional mode only. But in brittle material, that not will happen. That is the inference we can understand from this graph. Next, coming to the third one, a graph is drawn to express how the things are going to be happen for a ductile material and brittle material. Here, if you observe, it is a proportionality limit. How it is? This is the straight curve. We can observe that what happens for a brittle material, and that what same happens for a ductile material. Beyond it one, if you observe this one, it is also proportionality limit. Up to this from tensile strain is on the x-axis, on y-axis we have a tensile stress. So here, this is a proportionality limit. So from here also, if you observe the load, the curve is going to be like this. That is elastic limit, ultimate strength, and breaking point. These 3 points there. This is for a brittle material. Why? Beyond this one, the graph is not there. This shows this graph is drawn for the brittle material. At this point, if you remove the load, material lost its function. But here, if you remove the load, it will go on increasing its sagging is going to happen. That is the thing to be understand here. So in brittle material, sagging is going, but it is limited to function only, but does not failed. Here it is immediately failed. That is the third point to remember by observing this one. So what we have concluded from this one is, first conclusion drawn from this graph is, brittle material is going to fail at a ultimate strength only. Second one, ductile material gives a warning beyond ultimate strength. That is the second conclusion. Third conclusion is, brittle material has a sudden failure without giving any warning. Fourth conclusion is, ductile materials gives a warning before it is going to fail after its ultimate strength also. That is the fourth conclusion. If you observe from the graph, based upon the graph, we can conclude that the graph drawn, it is for the brittle material. So because beyond that ultimate strength, there is no graph is drawn. That is there is no stress bearing capacity of a material. That indicates that it is related to the brittle material. So these are the 5 conclusions which we can draw for this graph by using this slide. Next one is, and we have taken 3 definitions: elastic limit, proportionality limit, and ultimate strength. Next one is a ductile. Already you have learned this one, ductile. A ductile material continues to stretch beyond its ultimate strength without breaking, and the stresses decreases from the ultimate strength. So for a ductile material, beyond its ultimate strength, the stresses are going to be decreased. That we can observe for a ductile material. I repeat once again, ductile. A ductile material continues to stretch beyond its ultimate strength without breaking, and the stress decreases from the ultimate strength. Next, brittle. A brittle material has the ultimate strength and the breaking point close together. That means in a brittle material, ultimate strength and breaking point are almost one and the same. That is the thing happened for a brittle material. Next, if you observe other deformations for a material, there are other ways to deform a solid. 2 additional ways are shear deformation and volume deformation. Already we have explained the shear deformation, and volume deformation is concerned with the bulk modulus. Shear deformation. The forces act parallel to the edges of the solid. Tensile and compressive forces act perpendicular to the edges. So in shear deformation, what happened? The forces act parallel to the edges of the solid, and tensile and compressive forces act perpendicular to the edges. That is, shear force is equal to F by A. It looks like the previous definition, but the picture below shows the other. That is, shear strain is equal to del X by L. Del X is equal to change in length, L is the original length. Shear deformation, F is equal to force area. Next, if you observe this one, we are going, if you a palm, that is a hand is compressing a sheet. If you observe, it is one type of force acting, and this is one type of another types of force acting. So by compressing this one, it is going to be expand in these directions. So this way is going to be called as a shear deformation. So if you observe this one here, this is a rectangular laminate is given. Why? Because thickness is very low when compared to length and breadth. Here forces are acting on the top side of the laminate, and forces are acting on the bottom side of the laminate. Try to understand. L here, here dx is there, here is gamma is there. So if you observe this white color line, del x is equal to change in the deformation with respect to the original shape of this laminate. The change here also will happen. Whatever the change here, the same change is going to happen here also. That's why we have considered only del x. So for a shear modulus, capital S is equal to F by A into is equal to S into del x by L. We can observe the del x. What is the del x? Is the change in deformation happened here. So this is going to be called as a shear modulus. So shear modulus is also measured in PA. PM is pascals. That is, in Young's modulus, Pascal only. Bulk modulus also Pascal only. And shear modulus is also Pascal only. So what this inference you can calculate, or you can conclusion is, shear modulus is going to be change in dx value, and it is represented by the letter S. Bulk modulus is going to be volumetric difference. that is represented by K. Young's modulus is going to be the longitudinal strain that is represented by the Y. So already I have explained Young's modulus and bulk modulus. On similar grounds, we have you have learned about shear modulus. It is represented by the letter S. So volume deformation. So as in the this slide, if you observe, this have two conclusions. One is two deformations is possible. One is going to be the shear stress and shear strain, and one is shear deformation and volume deformation. For shear deformation, this is the concept you have to remember. For volume deformation, if you observe, as an example, consider a solid immersed in a fluid. The pressure exerted on all sides will change its volume. That means a volume is there, a material is there that is dipped in a fluid, and fluid tries to exert pressure on that specimen or on that object. So here this is a pink color object is going to be the dipped, and blue color is the fluid we have considered. And on this one, number of directions, if you observe, arrows are provided where force is exerted on the pink color object. Due to that one, the object tries to compress. So that is called as a volumetric stress is created by the pressure. So volumetric stress is equal to force by area. Here we have represented with capital P. The strain will be the change in volume caused by the pressure. That is, volumetric strain is equal to del V by small v. So the bulk modulus is defined in del P is equal to minus B into del V by V. Already in B we have represented P. So this concept already I told here. Here I am explaining once again with the help of a diagram, a schematic diagram here. That is, bulk modulus is equal to del P is equal to minus B into del V by V. Let the other moduli B is measured in pascals. Here we have del P is refers to the additional pressure above an atmosphere. Why there is a minus sign? Minus sign indicates here when the object is going to be compressed, we are going to take minus symbol. If it is going to be expansion, we are going to take a positive symbol. That is the thing to be understand here. So unlike the previous stresses and strain, volume stresses can be applied to a fluid. So del P is equal to minus B into del V by V. Here we can represent it with K also, because bulk modulus is represented with the K letter. Next. So this is bulk modulus concept, and this is going to be the shear modulus concept. Bulk modulus and shear modulus are explained in this two sessions. Let us have a problem on this one of the concepts. Here, a certain man's biceps muscle has a maximum cross-sectional area of 12 centimeters square. When it is converted, it is 1.2 10 to the power of minus 3 meters square. What is the stresses in the muscle if it exerts a force of 300 newtons? So what we have to calculate the stress. Stress is equal to force by area. Force is 300 newtons. Already area is given, that is 12 centimeters square. If we convert it into meters, it is 1.2 into 10 to the power of minus 3 meters square. That is 2.5 into 10 to the power of 5 pascals. So this is a simple problem. This is a fundamental problem which we can infer. Next one is a wire of 1.5 meters long has a cross-sectional area of 2.4 mm square. It is hung vertically and stretches 0.32 mm when a 10 kg block is attached to it. So when a block is attached to that wire, it is stretched 0.32 mm. Find stresses, strain and Young's modulus of the wire. So this is the similar problem what we have solved in the previous class, but it is given in a different manner. Try to observe here. Stress, you have to calculate stresses. Stress is equal to force by area. What is the force we are going to act on that member? It is 10 kg block. Area is 2.4 into mm square. So we can observe area is equal to 2.4 mm square. Try to convert it into meters. So we know that 1 meter is equal to 1000 mm. Taking this as a fundamental conversion unit, it is 2.4 into 10 to the power of minus 6 meter square. Next, what is the change in length? Change in length is given as 0.32 mm. Apply the same unit for conversion, that is 3.2 into 10 to the power of minus 4 meters. Stresses is equal to force by area. Force is 10 kgs into 9.81. Why? Because you have to convert it into Pascal as for a unit, that is conversion value 9.8. Then answer is 4.08 into 10 to the power of 7 Pascal. Next, strain. Strain is equal to change in length by original length. Change in length is 0.32 into 10 to the power of minus 4 mm by original length is 1.5 meters. That is 2.3 into 10 to the power of minus 4. As the strain has no units is needed to write here. Young's modulus. Young's modulus at the beginning of the class already I told F by L is equal, F by A is equal to Y into delta L by L. So F by A is equal to stress. Delta L by L is equal to strain. So Y is equal to stress by strain. That is 4.8 into 10 to the power of minus 7. Already we have calculated. Strain is equal to 2.113 into 10 to the power of minus 4. Thereby the answer is 1.92 into 10 to the power of 7 pascals. So if you observe students, in this class, total the following summary is there. 6 points we can remember. First point is how to calculate shear modulus, how to calculate bulk modulus. What is the difference between a brittle material and ductile material in terms of ultimate strength? That is the third point. Fourth point is we have solved two problems. One is regarding the calculation of stress. Second is regarding the stress calculation, strain calculation, and Young's modulus calculations. So this is the similar things, and you have observed a schematic representation of a how bulk modulus is going to be happens, and a representation of a shear modulus how it happens. So by this today's presentation is completed. I will provide the notes shortly, students. Have a good day. See you all. Have a nice day.